Okay, this is an introductory topic in physics, 1D kinematics. Here we're dealing with the physics of motion, and it's a scalar vector lesson. What's the difference between a scalar and vector? So that's what I want you to be able to know after today. What are some common scalars? What are some common vectors? And really what's the difference between the two? And then how to deal with them mathematically. So, and one thing to think about, looking at these pictures, this is a big part of the lesson. You notice how scalars, they're just a line. You can kind of see a length. You can see how wide it is in this case. Whereas vector, you can also not just see the length or the width here, but you can also see a direction. You can say, hey, this is an arrow. This goes from the back of the arrow to the front of the arrow. And so I know not just the magnitude, but I also know the direction. So kinematics, once again, is how objects move. This guy right here is moving in a straight line, one-dimensional, pretty much straight. A little bit more about one-dimensional, what it means, and how we're going to deal with some of the things mathematically. When we're talking about one dimension, we're going to talk about problems where the person's moving up, down, or maybe a little bit of both, but they're just moving along that one plane. So they're either moving up or down, or maybe both. Maybe they're going north 10 and then back south 5 and then north 20 or something. Or they're going left and right. So they can be going, as long as they're along this plane, they can be going either way. They could be switching back and forth, or they could just be going straight. I mean, as long it would still be one-dimensional motion if they were going straight. Next unit, we're going to go into two-dimensional motion. So just so you know what that is, if I talk about it, two-dimensional motion would involve something like this. You're going north and then you're going east. So really, you're not just going north and east, but you're going at this direction right here at this angle. So this direction here, and you got an angle right there. And this is where you're going to deal with SOHCAHTOA next unit. Or maybe projectile motion. It's going forward and it's falling. And the combined is 2D motion. And so we'll deal with that slightly different. But once again, it's going to be in the future when we get to two-dimensional motion. So scalars, you should think of magnitude only. And the magnitude is a number in a unit. If I say 5 miles or 5 inches, that to you should make a huge difference. I haven't set a direction. It alone is just a magnitude. How many slices of pizza? You can't put a direction on that. How many steps in front of the building? No direction. And so the main thing here is scalar quantities have no direction. Vectors, on the other hand, they're going to have the magnitude. In this case, it's 14 paces, not the normal meters or kilometers. But here we're just talking about paces. So 14 paces, that's going to be the magnitude. But then we include a direction. We know that they started in one location and they went north from there, 14 paces. So this has more information. Sometimes vectors can be applied. So if I know I'm going, in this case, I know I'm going from one place to another, represented by any arrow. That's why vectors are represented by arrows. I might use the word forward or straight. I mean, that you can apply. You're going from one place or another. You're not just saying the road was this length, but you're saying you went this far, or something did this. It could be implied. So in the way you can think about it is that arrow right there can represent a length and a direction. And if I was holding it and I didn't place it yet, it could be a lot. I mean, I could place it here. I could place it there. It's still a vector. It just hasn't been, I guess, defined yet until you place it down and say, okay, I actually did this. But it alone could be considered a vector. I went 15 meters forward would be a vector. So any of these ones right here could be, let's pretend like this is 15 meters long. This would be 15 meters, and here, that would be forward. That would be okay for a vector. Two common scalars are distance and speed. So those are going to be the most common ones that you'll see, especially on any sort of quiz or something, some sort of assessment this early. Two comparable vectors. When I say comparable, distance is kind of like displacement, but displacement has a direction. If you're dealing with things mathematically and there's more going on, you might have to do something slightly more. We'll see later on. And then velocity is comparable to speed. Except velocity, you're going to be going a direction. Speed, you're just going. So here, for example, distance is a scalar. If I say 5 meters, this is a distance. It has no direction. It's a scalar. If I say 5 meters and then I say east, I want 5 meters east, really for displacement, we're talking about how far we are from where we started. So it's not from the end to the beginning, it's from the beginning to the end. So displacement 5 meters east. And then speed, we're talking about meters per some sort of time. And standard units for physics are going to be meters and seconds. And so that's why if we use meters and seconds, then our speed is going to be meters per second. And then velocity is going to have how fast we're going, but in that direction. So 25 meters and then south. South is what makes this specifically a vector for velocity. So let's take a second, look at the problem set. Hopefully I provided a link for the PowerPoint on holdenclass.com. You can see this and you can go through it at your own pace. So I'm going to go kind of quicker. You can pause this now. 4 meters east, it has a direction, it has a magnitude, 4 meters, it's going to be a vector. The object was 4 meters, it's just saying how big the object was. It doesn't tell you a direction, so that's going to be a scalar. I had 6 donuts, that's also going to be a scalar. I ran 6 miles west of the river. I was running to the west. I was physically running to the west. That's a vector. I know the direction, I know the magnitude. I ran 1 mile forward. That's one of those tricky ones. I'm going somewhere. I'm starting at a location and I'm going forward from there. That would be considered a vector. The track was 1 mile long. I'm not physically telling you if you're going left or right along the track or anybody's even on the track. So therefore, it has no direction. It is a scalar. Nope. Okay, so no, this is an equation we're going to use a lot. Velocity equals, and this change in x represents displacement. If you get really particular, it's displacement along the x-axis, but we're going to use it for displacement anywhere. And then change in t is going to be time. And we could use this. We can use this. Scalars go with scalars. We can use this. It's practically the same thing. So if you look back here, v equals x over t. That's kind of like saying if you're just dealing with scalars, speed is equal to distance over time. That equation is comparable. So there's your equation. It's comparable to this. And velocity equals displacement over time. So if we're using the more information, the vector, to calculate the velocity, if we're using less information, scalar, distance, we can calculate the speed with that. So here's an example. Joan walks 4 blocks, turns around, and walks 2 blocks. She walked for 90 seconds. What distance did Joan walk? And so when I have my students, and if you're listening to this right now, write on their paper, distance you add up. If I ask you how far did you walk, you wouldn't care if you took a right and took a left and then whatever. You would just tell me how far you walked. You would add every single foot you walked together or every single meter you walked together. That's exactly what you do here. So this person walked 4 blocks forward, 2 blocks backwards. And therefore, we just add them up. I went 4 blocks this way and I came back and did 2 more blocks. So therefore, my overall was 6 blocks. No direction, because if you look back here, you actually went 2 directions. No direction involved. You just went 6 blocks total. So you add up for distance. For speed, you're going to just use, once again, scalars go with scalars. For speed, this took 90 seconds. So you're going to take that 6 blocks from before, and then you're going to divide that. So v equals x over t. Sometimes you see v equals d over t just to represent distance or displacement. But the displacement is, or in this case, the distance is going to be that 6 blocks right here, and it took 90 seconds to go. So you take that, here you go, speed is the distance divided by time, and always write out your equation whenever you can. Write out your variables, your givens whenever you can. So we plug it in, 6 blocks over 90 seconds, and here you have 0.067 blocks per second. So that's their speed. Once again, no direction. It's not how fast they went from the start. It's just overall. So before we get into any more physics about adding vectors, I want to kind of agree on something. Because right doesn't always have to be positive, but in math, most of the times you do have this coordinate system. But actually, before we get into that, let's look at this real quick. Here's an example where you would need to go ahead and add vectors. And you're going to have to do what I'll show you in a second. A man goes 2 kilometers east 2 kilometers. There you go, east 2 kilometers. Let's pretend this is east. And then west 1 kilometer. You're going to see this head to tail method. Anytime you draw the second vector, you always draw it from the end of the first vector. So you started here, you went 2 kilometers, and then you went back 1 kilometer. This is like you actually were walking it. That's why you put it head to tail. You don't go right back to the beginning. You went from here, you went to the end, you came back. You don't say, I went this way, and then all of a sudden throw the other vector from the start. It doesn't really work, and this will lead you into some proper practice. It will lead you into an easier time in future lessons. So back to this. So man goes 2 kilometers east and 1 kilometer west. What was the displacement from the origin? So displacement itself, I don't have to say from the origin. Displacement itself is from start to finish. Where did you go in what direction? So to go from here to there, how far was it in one direction? And looking at this, you can already tell me what it is. It's very easy. But sometimes you have more variables, more things going on. But physically, if you never even saw this picture, which is always a good idea to draw a picture while you do these, you would deal with it this way. So distance is how far did you, distance itself, so not displacement, distance itself is going to be how far did you actually walk. So here you went 2 kilometers forward, you went 1 kilometer backwards. That's what you walked. You went through 3 kilometers. Whereas displacement, you went 2 kilometers forward, 1 kilometer backwards. Displacement is really from start to finish, where'd you go? So this is what you'd have to describe for displacement. How far in what direction is this? This is your displacement. This whole thing is your distance. So this would be 1 kilometer east. Displacement should have a direction if you know it. Of course, the magnitude itself is 1 kilometer. The direction itself is east. Combined is the vector displacement. So for the math, this is what I was talking about earlier. For the math, we're only going to have up versus down or right versus left. We're not going to have these two mixed in, these up and right. That's going to be next unit. If you're going up, we'll call that positive. We'll go down, we'll call that negative, just like in most math classes. If we go right, we'll call that positive. If we go left, we'll call that negative. And we'll use that as a general guide to motion. In future lessons, it may make sense to say down is positive if something's falling, just on simple questions. But for now, let's go ahead and say up is positive, down is negative. Right is positive, left is negative. So let's walk through this problem, even though we had kind of already answered it. If you go 2 kilometers east and then 1 kilometer west, what was the displacement? Well, east does not get typed into a calculator, so we want to say east differently. In your calculator, since it doesn't know it, we're going to go ahead and use this east or right, in this case, is going to be a positive. So we're going to say this is not just 2 kilometers east, but this is plus 2 kilometers, which the plus is a place sign for that east. And then 1 kilometer west, we're going to go instead of saying west, we're going to look over here, we're going to say that's a negative. So now we call this adding vectors, even though we're going to be adding a positive to a negative value. But we're going to go ahead and plug that. Here's two vectors that we're going to add together. We turn the directions into signs, and now we can add them. And we go ahead and add them. When we add them, this will end up being what happens. And you're going to get a positive 1 kilometer. But positive might mean something to one person and something else to someone else. So we know that when we decided on what to use, we went over here. We said positive meant right or east. Since we were using east up here, there's only one thing it can mean. That positive stands for east. So we're going to drop that sign and we're going to turn this into 1 kilometer east. So that's how we deal with displacement. From start to finish, ignoring all that we did, we are 1 kilometer east of where we started. Okay, so here's your problem set. Dog walks 50 meters east and then 25 meters west. What's the distance traveled and what's the displacement? And the second one, a bird has flown 850 kilometers south from winter, and then he realizes he went the wrong way. It's still summer. So he travels 320 kilometers north. At that point in time, what's the distance traveled? What's the displacement? So just kind of getting at the basics here. Once again, distance is a scalar. Direction doesn't matter. You just add it up. So here's your first one. The first one for distance. For distance, you just added it up. You went 50 and then you went 25. Didn't matter the direction. You did 50 and 23. So your distance is 73 meters total. That's how far you walked. Displacement, how far are you from the beginning? Well, the dog walked 50 meters east and then went back 23 meters. Well, you're going to subtract that west has to be a negative. East we stood as a positive. We add those two together, so it's the same as subtracting 23 from 50. That answer ends up being a positive. At that point in time, we take away the positive and we say east. So this kind of cut a couple corners here, but 27 meters east is the displacement for that first problem. Second problem, we've got 850. Let me go back. 850 and 320. It doesn't matter which direction you went. If you went 850 and then you went 320, you traveled a distance, you just add them up, 11,070 kilometers. Don't forget the unit, and definitely don't have the direction. Sometimes if you're going the same direction, and not just this one, you switch from south to north, but if you went the same direction, the actual magnitude would be the same. You just don't want, for distance, you're never going to include a direction. Distance also would never be negative because of that fact. Displacement, 850 kilometers south is the same as negative 850, negative standing for south. And then 320 north plus standing for north for the math. We add those two together. That's the same as doing this, and we get a negative. The negative wins out. You'll end up getting a negative 530, and once again, this skipped a step. Negative 530, and then that negative has to be dropped and replaced with what it was in the first place, which was a direction, which is south. Don't forget the kilometers. Whatever unit you have in the problem is a unit you're going to have down here. Normally for physics, we're going to use meters, seconds, meters per second. We'll see acceleration later as meters per second squared. There's going to be a standard way we go about things. So here's your average velocity equation. If you take all the displacement and all the time, so the overall displacement and the overall time, that's going to be the average velocity. Another thing about this equation, if you see this equation, I can say that it for x, this change in x is the same as x final minus x initial. I don't have a visual for this, but let's say you started at this thing called 2 meters. You didn't start at 0. You started at 2 meters, and you went all the way from 2 meters to 5 meters. Well, you'd say 5 minus 2, and you'd say that change in x was 3. And if you say, let's say you were timing it and you didn't really, you started your stopwatch a long time earlier, and there's already been 10 seconds that went by, and it took, and at the end, your stopwatch said 13 seconds. Well, that you would go ahead and you'd look over here, you'd say, oh, 13 minus the 10, and this would be 3. So depending on what information you have, you might just do physically this in your head and then plug it in, or you might, you can use this equation many different ways. So let's look at 2 more examples. Here you have a car that traveled 500 meters north and 250 meters south in 1 minute. What's the distance, displacement, speed, and velocity? Just a little bit of practice. Should pause it, actually. I should be saying you should pause it, but there you go. This is the answer for distance. They just add up. It's going to be 750. Whereas displacement, you have to say north is positive, south is negative. You add them together, and you get a positive 250, and then you turn that positive into a north. Speed, now you're going to go ahead and take speed. Remember, you have to go back to this, and you have to look at your distance. You're going to use distance for speed, but that's going to take 1 minute. And so our unit here, because I don't tell you to convert, it's going to end up being meters over minutes or meters per minute. So speed here, take your distance, you take your time, and you just go ahead and put it into the equation, v equals d over t. Or v equals x over t, or whatever you want to call it. There's a couple different versions of it. The distance over time, 750 over 1, and then you keep the unit. So you keep your meters, you keep your minutes, and so it's 750 meters per minute. Velocity, we're going to go back here, and we're going to look at our displacement. We already solved for it, so we have everything we need. Look back at the displacement. It was 100 or 250 meters north was our answer before, and we're going to take that and put that over. So we take the vector for vector velocity, we take the vector displacement. We'll still use the same, we'll still have the same unit because this also has meters and minutes, but here we'll have the direction north. So if you're changing directions all the time, your magnitude for velocity, for distance, displacement, velocity, and speed are going to be different. If you're going the same direction the whole time, your magnitude would actually be the same. Then the last one, if your car travels 100 meters east for 5 seconds and another car travels 80 meters west for 4 seconds, what's the velocity of each car? Is the speed the same for each car? This is a good question. Is the velocity the same? So, should have paused it. Once again, I missed that. But if you didn't pause it, here you see the answer ready, so don't look at it. One car going 100 meters east in 5 seconds. We'll go ahead and say this is positive because it was east. I should have put a little plus sign, even though you don't really need it, but the plus sign represents east. And you take the velocity equals the displacement over time. 100 over 5, you get positive 20. The positive stood for east. So here you have 20 meters east. Second car went west, so it was negative 80, and it took 4 seconds. So we solved for v. V equals what? V equals, and it ends up being x over t, just like here. The displacement was negative 80, and the time was 4, and you get negative 20 meters per second, and the negative stood for west. So here are your answers for velocity. One car went 20 meters per second east, the other car went 20 meters per second west. So is the speed the same? What you want to do for speed, direction doesn't matter. So just get rid of east, get rid of west, pretend like they're not there, and just look at the numbers. Is 20 meters per second and 20 meters per second the same thing? And the answer is yes, they are the same. Ignore direction. Is the velocity the same? No. East and west are two different things. If someone tells me to go 20 meters per second east and I go 20 meters per second west, am I going to end up where I need to go? There's no way. So that's going to be important. For velocity, east and west are going to be two different things. And so they would not be the same because you ignore direction.